Okay, okay, so let's continue from last time. We were doing some problems. We finished the velocity selector topic. Is there any questions from this entire chapter? Any questions?
No, sir.
No questions? Okay, so today we'll start a new topic from this chapter, which is called the Hall's effect. Okay. So basically, consider that you have a slice, a conductor basically, and I'm going to draw it something like this, right? And suppose it has some thickness as well. So let me draw that. Right. So let's say that this is the thickness of the conductor T. There is some current that flows through the conductor. Let's suppose that it flows in this way, right? So this is the current I, and the length L is L of this conductor. Let's use capital L. Okay, so this is the picture that we have, and what is happening in terms of the flow of electrons in this figure. So basically, if I look at a top view of this, then I have something like this, right? Well, let me draw it again. Well, something like that. Now, the current is going in this direction, which means that I have a lot of electrons that are flowing, that are moving with some velocity v in this direction. Okay, so this is an original scenario. What you can do to this is perturb it by applying some magnetic field, right? So now we apply a magnetic field in such a way that it is perpendicular to this surface, perpendicular to the surface area, top surface. So again, what I'll do is I'll just take this, copy this. Let's put it in. Okay, so apply some magnetic field. Let's suppose that it is applied in this way, that it is perpendicular to the conductor, but it's in the downwards direction. So the magnetic field is applied inside the conductor. What would you expect to happen in terms of the flow of electrons? Again, if I draw a top view, what would you expect the flow of electrons to be? Again, the current is still in this direction, right? So the magnetic field is just applied across this conductor. Outside, there is no magnetic field. So what would you expect the electrons to do? Anyone? No idea?
They will experience force.
They'll experience force, right? So when they experience force, their direction will change, and you can find this force by using the left-hand rule. And this force will be in this direction. Let me draw it. So the electrons will experience a force in this direction, So the path of the electrons, if I draw that, would look something like this. Okay, so this is the path that they'll take. Which what does this mean? These are electrons, right? So you can see that they're moving towards one side of the conductor. If that happens, the other side of the conductor, electrons are lost from that side. You can say that if there were electrons sitting over here, then those electrons have been moved to this side, so there is nothing left over here. So if this side is has more electrons, it becomes negatively charged, right? And consequently, the opposite side, where there are holes, sometimes we call them, so there is no such thing as, I think I've mentioned this before, as a real positive charge, but it's just that there are no electrons in that specific region. So it is just the electrons, really. uh, if there are no electrons in in a specific region, we call it that there is a hole over there, and the hole is positively charged. So this side then becomes positively charged. Okay, the magnetic field is again into the page, so I'll represent it with a cross. So now you see that we have a net negative charge on one side and a net positive charge on the other side. So what happened is that because of the application of the magnetic field into the conductor, these charges experienced a force, and this force is a magnetic force, and they were deflected to the left. And that left us with a negative and a positive charged sides. Now, what happens when you have this arrangement of negative and positive charge in terms of fields? You'll have an electric field, right? An electric field will set up such that it, so the electric field will be from this side to this side. So this is from positive to into negative, right? So these are the lines for the electric field. Okay, so up until this point, everyone agrees with what's happening?
Yes, sir.
Okay, all right. So if there is an electric field that is induced in this way, we know that there will be some potential difference across this conductor, as in some potential at this point, and there is some potential at this point. Let's call this positive, and this is V minus. So this is there is some net potential difference between these two sides. So the segregation of our electrons on one of the side had, you can say, induced a net positive charge on the other side, and that induces a potential difference across that particular side of the conductor, right? So this potential difference that is induced is called the Hall's voltage. So the induced potential difference due to segregation of charges is termed as the Hall's voltage. And this is essentially the Hall's effect, right? Now, so what would happen is, if I attach a voltmeter over here, right, and I connect it to these two sides, I'll have a reading on this voltmeter, and let's call it VH for Hall's voltage. Okay, now what is happening? There are only two forces at play in this scenario. What are those two forces?
Electric field and magnetic field.
Yes, so we have electric force, let's call it Fe, and we have a magnetic force. Okay, but should we not have one more force, which is usually always there? Which
Gravitational.
is that for? Sorry, again?
Gravitational.
Gravitational force, yes. So the weight, should we not have that as well here?
Sorry, there's a very small mass, so it wouldn't matter.
Exactly, right? So we have mentioned this before as well, that the gravitational force is extremely weak compared to the electromagnetic force. And so even if I were to include, well, in reality, yes, there is some gravitational force, let's call it Fg, and that is the weight of these electrons, but it is so small that if I write an equation for a sum of forces, right, the Fg would be so small, it would be of 0.0000, a lot of zeros really, and then some number. So it doesn't make a difference if you add that small amount into something, so we can completely ignore that. So there are only, then we are left with these two forces. So if these are the only two forces, then they should be balanced by each other, which is if I write the resultant force equation for this, it is the magnetic force is equal to the electric force. Now, let's call FB as the magnetic force. So now what I'm going to do is, my goal is to derive an equation for Hall's voltage, this potential difference, right? So we want an equation for VH, right? So to see how does our Hall's voltage depends on the geometry of the conductor, on the current that is passing through the conductor, the magnetic field that I applied on its strength, right? And well, number of charge carriers as a number of electrons in this case, right? So we'll start with this relation that we have, that the magnetic force is equal to the electric force. That means that QV B is equal to QE. You can immediately see over here Q's cancel out, and you're left with BV is equal to E. Right. Now, what is this E? This E is the electric field, right? And in terms of a potential difference, we all know now that electric field is the ratio of the potential difference across the plates divided by the distance between the two plates. In this case, the plates are behaved as in these two sides, right? So it is the distance D will be then this distance in the figure. Okay, so what I can do is I can take this and put it in this equation. So I get B times velocity is equal to V, which is the voltage, over D. Right? Again, well, let's eliminate that misunderstanding right away. Let's call this V as Hall's voltage, right? Because we know that the potential difference that is being induced due to this thing is called the Hall's is coming from the Hall's effect, and so it is just the Hall's voltage. Okay, so then what we have is this thing, and you can rewrite this equation for Hall's voltage as BV times D, right? And so this is my Hall's voltage, right? And what I can do now is I can find a relation for this velocity, which we already have. And we can use that relation in this equation to see how does the Hall's voltage depends on the current, right? So you're familiar with this thing that we have V is equal to I times R. So there is really a relationship between V and I, right? And R is a constant that is being multiplied with this, which is really the resistance. So in exactly the same way, let's try to write an equation that looks at least similar to this one. Right? So let's look for that. Now we know that the current is given as N A velocity times the charge, right? Where again, N is the number of charge carriers, V is the velocity of these electrons, E is the charge of the electrons, and A is the cross-sectional area of your conducting surface, right? So you can rewrite this equation as V is equal to I over N A times E, right? And now I have an equation for velocity. Let's take this and throw it in that equation, and we get, let's write it down over here. We get Hall's voltage is equal to B times I D over N. What is A, right? If you look at this figure again, this is the thickness T, right? This is the length L, and this was the distance D, right? So if these are positives, there is negative over here. So it is this, it is this surface whose area we are talking about, right? And this is what makes A. So A is then really just the thickness of this conducting surface times the distance D. So I can rewrite A as A is T times D, right? Because it is a rectangular geometric shape. So the area is just the product of two of the sides. So we can take this and we can put it also in this equation. So this becomes D times T, and then you have the charge E. So you see a D cancels, and Hall's voltage is equal to B over N T E, right? And then you have I multiplied by I. So this is the equation that we were looking for. And this is an equation that looks similar to the equation that we usually know, V is equal to I times R. So here also we have a relation between V and I, and here you can see a relation between V and I. This term B over NTE behaves as a resistance to this Hall's voltage, to the electrons flowing in this way, right, in that particular direction. Okay, so any questions so far?
No, sir.
No, sir.
All right. So this, let's see what is some of the things that this equation is telling you. First of all, it's telling you that if I apply a stronger magnetic field, we get more Hall's voltage, right? So which is just that the Hall's voltage is really directly proportional to the magnetic field. If I increase the flux density, the Hall's voltage that is induced is high. And let's say if I talk in terms of these number of charge carriers or the number of electrons, if I were to decrease the number of electrons, you can see from this equation that Hall's voltage increases. So now I'll just write it like this. So if I decrease N, then we can see that we have more Hall's voltage that is being induced. And exactly the same thing happens for the thickness of the conductor. If I decrease the thickness of the conductor, I get again more Hall's voltage induced. So again, sometimes this effect is happening due to the magnetic field, and you would like to determine a Hall's voltage that is induced. So in that case, we prefer to use a conductor who has a less value for the number of electrons and also a thin slice of conductor. Right, so the thickness would be less for that. Having these conditions met, you will be able to measure the Hall's voltage. Otherwise, it would be really small. We might not be measurable, right? Okay, so any questions so far?
No, sir.
Is the concept of Hall's voltage clear?
Yes, sir.
Okay, all right. Okay, so let's move forward. Okay, let's start. Now, how can you experimentally measure this thing, right? How can you experimentally determine what is the Hall's voltage that has been induced, right? So what we use for that is a device that is called Hall's probe, right? And using this device, we can measure the induced Hall's voltage. So it is really a sensing device. Let me write it down as a bullet point. So it is really a sensing device. It senses the magnetic field, right? The magnetic flux density. So measures magnetic flux density, which is just B, the magnetic field, right? And so measuring the magnetic flux density gives us a value for Hall's voltage. And what we can do is we can take this Hall's probe. So let me draw. Again, the Hall's probe is made of a very thin sheet of material. Again, why is it made up of a thin sheet? The reasoning is coming again from this equation that we saw over here. To get any measurable Hall's voltage induced in the conductor, you require a small thickness, which means a thin slice, right? So this a Hall's probe is usually made up of a thin slice of a conductor. And what you will do is you'll take this Hall's probe and attach it to what is called a CRO, cathode ray oscilloscope. What this will do is it will show you the induced Hall's voltage. Right, corresponding to the to that value of magnetic flux density. So how do we use this Hall's probe. The first thing is that the Hall's probe is not the Hall's probe, but again, as we started off, the magnetic field lines are perpendicular to the slice of the conductor, right? So if I let's suppose that this okay, so I have to draw this thing again. So suppose this is my conductor, and as we saw previously that the magnetic field is, so this is coming at, how do I draw this? Actually, I need to draw 3D figure. Okay, so we have a magnetic field that is coming like this. That was perpendicular to the surface. What if it's not perpendicular, right? So suppose if the magnetic field, if B is at an angle, in that case, what we'll have is, let me draw this. Suppose the magnetic field is, so this is the normal. Let's draw it like that. So this is the normal from the conductor, and the magnetic field is applied at some angle to this normal, some angle theta to this normal. Why we choose the normal line to the conductor? Because the magnetic field that we require to induce the Hall's voltage is only the perpendicular component of that magnetic field, right? So we just measure, so this is the magnetic field, we just measure the angle from that normal and then just include the sine. Well, in this case, that component is it, because it's the angle is with normal, so this is B cos theta, right? So the side which has an angle, it is a cos component. So okay, so if it is like this, then only B cos theta component is responsible for inducing Hall's voltage. So what would you expect the Hall's voltage, the induced Hall's voltage to be? Would it be greater or would it be less compared to if the magnetic field was exactly perpendicular to the slice? The induced Hall's voltage will be
Less.
Yes, exactly. So it will decrease. Again, it will decrease because the total magnetic field is B, which will have two components. It is made up of two components, right? The cos component and this one, the sine component, which is this side. So let me write it B sine theta. But the component responsible for the inducing Hall's voltage inside this conductor is the perpendicular component. Again, if you're confused, why is that so? If you go back in this figure, only if you apply it perpendicularly to the to this slice that is of this shape, the force on the electrons will be in such a way that it will cause one of the it will cause electrons to be combined, I guess it's not the right word, but sit on one side of the conductor while the other side then becomes oppositely charged to the electron, so it becomes positively charged, and this will then induce some voltage because of the difference of the potentials at these two sides, and that is Hall's voltage. So again, it is the perpendicular component of the magnetic field that is responsible for even inducing the Hall's voltage. So so that's why it is the perpendicular component, and so some of the magnetic field is lost if it is applied at an angle theta, right? Lost in a sense that only a cos component of that magnetic field is responsible for inducing Hall's voltage, while the other component has no role. So it is just neglected or ignored, right? So well, that's most of it. There is well, there is nothing really more to this topic. So in the next class, we'll start with what is called quantum physics, and yeah. So I guess we'll just end this class over here. Right? Any questions from this topic? Did you all attempt the quiz that I gave you on charged particles? Is there any questions from that quiz?
No, sir.
Okay, so well, there's one thing. Let me just open one of your quizzes, and let me just tell this one thing quick. 1 second. Okay, so there was a question. Let me go to the next page. There was a question where we had plates like this, right? And so this was positively charged plates, and these were negatively charged plates. So the first part, well, it was very simple, that you had to draw electric field lines, and which would be in this direction, right? So I'll just draw 3 lines like this. Then I told you that you have multiple particles, right? So we had an electron, we had a positron, we had a neutron, and we also had a proton. If I remember correctly, these were only the particles. So it was asked to show the direction of deflection of these particles when they pass through this electric field. And well, most of you got it right. Well, all of you got it really right, except for one little thing that not everyone got it right, was when I was drawing the path of these two things, right? You see that both of them, excluding neutron, both of these things are positively charged. But there is one difference between the two. A proton is heavier than an anti-electron. Anti-electron is just an electron, but with a positive charge instead of a negative charge on it. And the mass of the electron is very less compared to the mass of the proton. So the path that I would draw for a positron, if it is, well, not for the positron, for the proton, it will be deflected less compared to if I were to draw a same path. Let me draw on top of this. Compared to this one, where this is a positron. So E plus, and this one is a proton, right? So the positron will be deflected more compared to the deflection of the proton, because proton is heavier. It will be very difficult to change the inertia on the proton compared to the inertia that is coming carried by the positron. So is that clear?
Yes, sir.
Okay, all right. So yeah, let's end this class with this, and in the next class we'll start with quantum mechanics. Well, really quantum